So, first let's talk about the homework. Well, actually, everyone, please turn on your camera if you have one. Okay. Anyway, so this homework was a bit harder than usual. And I think it's because people mainly didn't really understand the counting stuff. So, um, I'll just go over it again and talk about what are probably some common errors people make. And first, like, the most common error, I think, is don't confuse factorials, combinations, and permutations. Like, they all do similar things. They're all counting the ways to do something, or like to choose them. But it's very different. And you have to make sure that everything is that you use everything in the right one. So a combination is if you want to select things, but that doesn't require an order. A permutation is if it does require an order, and a factorial is if you're ordering everything. So for the first one, how many ways are there to get from the bottom left square to the top right square, going up and right? Does anyone have any idea on how to do this problem? Okay. Oh. So if we just try and draw a path from start to the end, so you move, uh, so it doesn't really matter which one because you'll see that because you can only go up and right. You can only have the same moves, just in a different order. So does that make sense? Uh, so if we just draw something this, you can see that you have 7 right moves and 1, 2, 3, 4 up moves. So what this means is that you have to find a way to choose 7 right and 4 up. So there are multiple ways to do this. The first way is to just directly order it, right? So remember that letter rearrangements. So 7 right and 4 up. That means that we need to rearrange the letters in R, U, 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 U. So we're just representing the moves we make as a string of characters. So like if we take this path, for example, just like a random one, and this would be represented as R, U, U, R, U, R, U, R. Anyway, uh, we want to find the ways to order this. So there are obviously there are 11 letters here. So 11 factorial is the number of ways you have to order them. However, of course, we're counting each one multiple times. Specifically, the amount of times we have to rearrange just the R's and then just the U's. Because there's 7 of these, and it's going to be 7 factorial and similarly 4 factorial. But you'll notice that this is exactly the same formula as 11 choose 7 or 11 choose 4. And the reasoning for that is if we instead of thinking it as 7 right and 4 up, you can think of it as 4 up per 11 moves. And the 7 remaining moves will have to be right because we don't have another option. So this will give something equivalent, which is in this time, we're just choosing 4 out of the 11 moves to become an up. And the reason why we don't want them to have an order like 1, 2, 4, 7, if we choose the first, second, fourth, and seventh one to be up, um, we this is the same order as if it were 2, 4, 7, 1. So we don't really care about the order as long as it's the same ones. So that's why if you just choose 4 of these, for example these, that's how you can make a path. And again, you got this, which is 10 times 9 times 8 times 7 divided by, oh wait, 11, sorry, 11 times 10 times 9 times 8 divided by 4 times 3 times 2. These cancel, this cancels, and you got that's 330. Does anyone still have a question on number 1? And I mean, uh, uh, if most people got this one, although some people did have trouble with it. The next one, I think people may have had less idea because I didn't go through it thoroughly in class. But how many rectangles can be formed by tracing the lines in this grid? Well, if you count these, for the problem on the last homework, which was much smaller, only like a 2 by 3, you're able to just use casework by the size of it. However, obviously this one is too big to do that. If you do it, it would probably take hours, maybe even like a day. So instead, okay, uh, uh, um, okay. Chenka asks, why is this one not 4 factorial, 10 factorial? I will explain that later. But you can count uh that, like for example, there. Remember from last class that if we just choose any 2 vertical lines and 2 horizontal lines, it'll of course make a rectangle between them. So if I take this one and this one and this one and this one, if we just draw them out, uh, well, you can find that the rectangle we got is going to be the one bounded by them. So it's this one. And you can make one for every single line, and every single rectangle, no matter how you draw on it, will correspond to one of those choices. So in this case, it's between choosing the first line and the last line, the second line and the last line, sorry, and this one and this one. And this is what you call a bijection. Like it's when you have something that corresponds one-to-one with another thing, where one element of it directly corresponds to another, to one and a different one. But anyway, the number of ways you have to choose the top and bottom one uh, uh, is going to be 5 choose 2. And the reason why it's not 5 times 4 is because if you choose this one as a side and this one as a side, it's the same as choosing this one as a side and this one as a side. So the order doesn't matter. And if you count, yeah, and if you count these, I believe there are 11 of them. 11 of these horizontal lines, I mean vertical lines. So it's going to be 5 choose 2 times 11 choose 2, which equals 5 times 4 divided by 2, 11 times 10 divided by 2. You can cancel things and you get this equal to 550. So I received a question, why is this not 4 factorial, 10 factorial? That's because factorials aren't really meant for this purpose. If you recall, a factorial is the number of ways you have to order some set. So we're not ordering these 4 rows right here. We're just choosing some amount of them to be bounded. And the reason why we use 5 choose 2 and not 4 choose 2, which is another common mistake, is because if we were using 4 choose 2, as in we choose like some of these boxes instead, we would miss out on some on rectangles that are either 1 wide or 1 tall. So because then you'd be choosing the same one twice, which is not something you could do using combinations. So does anyone still have a question about this? There are 10 options for one wide, 9 for two. Okay, but you have to, but you gotta, you, okay, hold on. You need to remember, what, okay, so if you have 10 options for one wide, 9 for two, etc., you have to remember that, well, okay, I'll use the other one since it's smaller. So, so four options for one tall, three for two, uh, two for three, and one for zero. One for four. I agree that you do have these options. However, remember that you only multiply them if they're like uh, if you're finding the ways you could do A or B. But of course, you can't. Your rectangle can't be both one tall and two tall. So that's how you don't multiply. If you're multiplying four times three times two times one, uh, and like you choose one, you might get the one that is somehow also this, while also this, and this and this. It doesn't really work out that way. Instead, you have to add them because again, there's no way you can be both one wide and two wide, and then that's where you get 10, and you'll see that 10 is just equal to 5 choose 2. So uh, that's another way you could do it, but you have to add, not multiply. And then after that, you could get that wide. You have 55 options. One, well, yeah, one plus all the way to 10, and then from there you can multiply these because you have to choose one thickness and one little height and one width. But you can't like choose one tall and one too tall. So does that make sense? And does anyone still have any questions? Okay. If nobody has any questions, we could go on to the next one, which people also had some trouble with. So the way you want to do this problem is instead is well, like you might think, okay, well there are actually multiple ways you could do this problem. The first way is, well, if you just draw any triangle here, well, you have to do this for both methods, but you can see that I'll use a different color, this. No matter what triangle we draw, if we instead just extend all of them, extend all the lines, you can see that no matter what, we're going to have three of them, which is obvious because it's a triangle. And more importantly, you'll see that these lines, the only lines in this grid are the ones emanating from these points. So of course, uh, one. Okay, so if you're just choosing three lines, then that would give us a triangle. However, the issue with just choosing three lines is that if you choose three of them that are all from here, for example, if you choose this one, well, if you choose this one, as well as this one, you wouldn't be able to form a triangle because all of these go to the same point. So that's why you can. Sorry, can you hear me now? Okay. Instead, you have to subtract the number of. Oh, okay. So first, let's just choose three lines. So if there are 10 lines in this diagram, five from here, and that's going to be a total of 10 choose three. Well, uh, it's going to be a total of 10 choose three, which equals 10 times 9 times 8 by 3 times 2, and you can get this equals 120. However, like I said, the issue with this is you can't choose three from the same one. So how many ways are there to choose three from this one? Okay, so someone asks, what does number choose mean? Okay, so if I have something like N choose R, that's just a way to verbally say uh, this or this or um, this. Those are be the same thing, and is again it's just a combination. So it's a number of ways to choose R from N. Uh, no order. And again, the calculation for this is n factorial divided by n minus r factorial. But the better way to think about it is simply something like if you take a 7 choose 3, we take the three numbers, um, well, the three numbers down starting from n, so 7 times 6 times 5, and divide by 3 factorial. And you can think of this as, again, if we're choosing 3 from 7, we have 7 for the first, 6 for the second, 5 for the third, and then we divide by the way we have to order all of them. And it has some really interesting properties that are more advanced. But anyway, uh, for this one, for example, if we're choosing 5 from here, that's going to be 5 choose 3 because we're choosing 3 objects for 5 and we don't necessarily care for the order. So that's why we subtract by 5 choose 3 and another 5 choose 3 for the right side. So that's equal to 120 minus 10 equals 100. Another way you can think about this is, uh, well, if you, well, another way you could think about it is that you must have 2 from one of them and 1 from the other. That's just how, like, well, they have to add to 3 and they can't be 3 and 0, so it has to be like that. So if there are 2 from here and 1 from here, you have 5 options for the one from here. 5 choose 2 from the one here, for the ones here, because you have to choose 2 lines from these 5. So it's going to be 5 choose 2 times 5, which equals 50. But of course, you can also have 2 from this side and 1 from this side. So that's why you multiply by 2 and you get 100. Does anyone have any questions about these three problems? If not, then we're going to continue on to the content. So again, this is what it is: C of n comma r, or ncr. I realized I wasn't this careful before. I didn't say it out loud, but you say this as n choose r, not like n combination r or anything like that. Just as a shorthand. Um, okay. For I have a question. Can you do the add method? I'm not sure what you mean by that, but I think you mean for something like number 1, where there's one way you can go from, like, it's only applicable to these grid type problems, where you have one way to go to each of these because uh well, you could only go them by right or up. You have 2 from here because you're there, and so on. 4 plus 3 plus 2 plus 1, 5 times 2. Um, okay. Okay, yeah. So 4 plus, well, okay, I see what you mean by the add method. So, what the person who has this question is saying is that instead of choosing, like, if we're choosing this side, instead of choosing just 5 choose 2 directly, because you're choosing 2 from 5, we can instead choose 4 plus 3 plus 2 plus 1. So this one is going to be, if you're going to choose the largest gap, if you have one that's 4 and 1, and then this is going to be 2 because you have this one, and so on. And yes, you can do this. However, it does the exact same thing as simply using a combination. And oftentimes, I guess it could be easier, but if you have really large ones, like this one, like this one where you have a 4 by 11 and you have to add all of them up to 11, or a 5 by 11, it's a lot easier just to use combinations and just like get into the habit of it. And again, you can see that it's exactly the same thing. So yes, you can, but you might not necessarily want to. So again, choose just means combination, and the way we calculate it is just, how did I get minus 20? The minus 20 is for the other method, where you just choose 3 from them. And the reason why we need to subtract 20 is because there's a chance, uh, because 20 of these 10 choose 3, where we're just choosing 3 of them, will involve choosing 3 lines. Like, for example, we might choose this one, and this one, where they all have where they're all from the same point. And if you have any 3 lines from the same point, you can pretty easily tell that they won't be able to form a triangle. So there are 10 ways for each of these, because 5 choose 3. We're choosing 3 of them from each group of 5, and you multiply that by 2. If you're just directly multiplying, you won't have that issue. Because, well, if you're using the other method, you won't have that issue, because you are just not going to have the case where 3 of them are in one and 0 on the other, because you already are only counting the ones where you have 2 and 1. Does that make any sense? All right. So actually, if you have any questions, you could just, instead of like going back and forth, if you're in the middle of typing a question, you could just type a question mark in chat, in private chat, and then I'll know to like wait for you to finish typing. So if that's easier for you. But anyway, again, uh, let's go to this example. Combinations are basically the most important things uh, in counting, and if you just take a look at this problem, you can see how you make it. So if you have 50, so you have 15 people in the class and you want to form a 4-member committee. You have 15 options for the first member, 14 for the second, 13 to the third, and 12 for the last one. But of course, because they're just a committee, they don't have an order. So if you choose students A, B, C, D, it's the exact same as students B, C, A, D. So then we have to divide by the number of ways you have to order these students, which is simply 4 times 3 times 2 times 1. So this is always the way you get a combination. And the formula is, uh, well, if you're just doing a calculation, then like directly with multiplications and division, it would be easier to do it this way. However, the formula is mainly there. Um, eh, it's mainly there if you have to do like more complex stuff where you can't multiply directly. Like if you're multiplying 2 combinations together and and like it cancels. And of course, the way you get this is that this one is clearly just 4 factorial, 4 times 3 times 2. This one is the start of 15 factorial, but 15 factorial also has 11 times 10 and so on, which would be 11 factorial. So that's how you get that. And again, this is the exact same thing as saying n choose r. So this equals 11 choose 4, 15 choose 4 actually, which equals 15. And this is making people write it. But if you can't do it, you can just write 15C. Anyway, again, the formula is not really there. It's a lot more important when it comes to counting. Instead of memorizing formulas, is to memorize how things work and to like get the concept behind it, because you'll often see like slight variations of combinations or something. So remember, grid paths, rearrangement, and position choices. We talked about this one for the homework. And again, use combinations. Uh, use combinations when for this one. It's similar to the triangle one. We're choosing 3 of them, but in this case, they can't all be on the same line. In that case, you can't all come from the same point. This one again is like the other problem. We have to choose some vertical lines and some horizontal lines. Complementary counting. I alluded to this last time, but I never got to fully talk about it. So the concept of complementary counting is really simple. All we're doing is finding the total number of outcomes and subtracting the outcomes we do not want. And if you think about it, we already did that on this problem and the number 3 on the homework. Because in those cases, we're finding the ways that we could get any 3 points, and then we're subtracting the ones we don't want. In these cases, the ones that we don't want are the ones that don't form triangles, or that don't form. Oh yeah, in both cases, they don't form triangles. So in many problems like this one, for example, it's going to be slightly easier than counting directly, because otherwise you have to get into casework and it's kind of annoying. So how many 10-unit paths from A to B do not pass through X? I'll just go through this myself. And you can try the next one using. So, how many 10-unit paths from A to B do not go through X? Well, how many ways are there to get from A to B in general? So you have to, 1 right, 2 right, 3 right, 4 right, 5 right, 6 right, 1 up, 2 up, 3 up, 4 up. So, we have 10 moves. Well, 10 moves, it tells us that. And 4 of these moves has to be up. So 10 choose 4. And, but remember, we can't have them pass through X. So how many paths do pass through X? If you think about it, it's the exact, if we just partition these, it's like split, that, we have, it's the same as finding the ways to go from A to X and then from X to B. There's no way to like find to move anything else or whatever. You can see that that's the case. So from A to X, we have 4 moves, and 2 of them are right. 2 of them are up. So this is going to be 4 choose 2 because we just have to choose 2 of the 4 moves to be up moves, and multiply this time because you have to go from A to X and then X to B. So you have to choose 1 for both, not 1 from both. And in this case, we have 6 total moves from X to B. 2 of them are going up, so it's going to be 6 choose 2. And if we just do the math, 10 times 9 times 8 times 7, divide by 4 times 3 times 2, this cancels, 2, 10. 4 choose 2, 4 choose 2 is equal to 6, 6 choose 2 is equal to 15. So the product is 90, so it's 210 minus 90 equals 120. So that just shows the basic concept of complementary counting. We find the total number of ways to get from A to B, and we subtract the ones that do pass through X. So for this problem, we have to find the total number of ways to just flip a coin 8 times, and we want to subtract the ways that he flips either 1 or 0. So does anyone? So can everyone just think about this problem for about 2 minutes, and if you have any, if you have any leads or if you like have an answer, then please just send me a private chat message. So. Okay. You don't understand the problem. Okay, so Paul flips the coin 8 times. So if you have this, then you're going to have possibilities like H, 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 T, 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 or H, T, H, H, T, H, 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 or T, 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 T. And, sorry. I did make a mistake here. I'll correct it on the later copy, but this should not be coins. It should be heads. So heads. Sorry. So in this case, we'd be counting this one and this one, but not this one. So we're just finding the ways that you can flip at least 2 heads. And again, the best way to do this is to find the number of ways he flips the total and then subtract the ways he can flip 0 or that he can flip 1. That is a lot more straightforward. Okay, I corrected the issue. Okay, if you have a question for the first example, please write it out or speak up if you want to. How do you find the number of possibilities that go through X? Okay, so the way you do this is if we consider, um, let's consider how something would pass through X. So an example with this would be, for example, this, well, uh, this. Oh, I'll use a different color. This. And you can see that no matter how you draw it, because it goes through X, and 10 units is the shortest possible, that means you can't backtrack or go left or down. You have to make it from A to X and then from X to B. And again, using only up and right. The number of ways you can get to X up and right from A is 4 choose 2, and from X to B is 6 choose 2, so we can multiply them. And the reason why I multiply them instead of add them is that for one way to go to X to B, and we have 6 ways to get from A to X, you can do them in any order. So you can have this one, but you can also have this one, or this one, or this one. So I hope that makes sense. But it's been some time, so we're just going to go over how you're meant to do this problem. So first, if Paul flips a coin 8 times, how many total possibilities does he have? The total in this case is just going to be 256. Does everyone see why? Because you have 2 options for the way a coin lands, and you have 8 of them, so 2 to the 8th power. or 2 times 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 2, which equals 256. And how many ways can you flip at least two heads? So we're using complementary counting. Using K-string to find the number of ways you can get 2 and 3 and 4 and 5 and 6 and 7 and 8 is going to be really annoying. So instead, what we're doing is instead what we're going to be doing is subtracting the number of ways you can get 0 or 1. So the number of ways to get 1 to get 0 heads is just going to be 1 if you get all tails. If the number of ways to get 1 head is simply going to be 8 if you have the tails. If you have 1 head and then all tails, 1 tail. If the second one is heads, if the third one is heads, and so on. So our answer will just be 256 minus 8 minus 1, because you can either have less than 2 or more than 2, or at least 2. It's 256 minus 9, which equals, well, 2, sorry, it's 256 minus 9, which equals 247. So I know someone put like 3,500 and 84. Can you explain how you got that so I can see, like, I can show you why that's, uh, so I can see what you did wrong? Okay, 8c2 times 2 to the power of 6. Um, let's see. Okay, I think I sort of see what you're doing here, what you're trying to do here. So you're trying to first fix which two, uh, you're trying to first choose 2 of the 8 to be selected as a head, and then find the other ones. The issue with that, though, is you got overcounting, and it's not just overcounting, you can divide because it's inconsistent. So an example is if you have something like H, H, T, T, H, H, T, T, you can, if you choose these, well, let's just take a look at how many ways this is counted. If you choose these two from the A choose 2, then that clearly works, but you can also choose these two, or these two, or these two, or these two. And either way, you would count all of those because you're doing 8c2 times 2 to the power of 6. And another way you could tell that you can immediately tell that's wrong is that the total number of ways is only 256, which is 2 to the power of 8. So there's no way that it can be more than that. Does that make sense? Okay. And uh, so then right now, actually, we could have a 5-minute break. So come back at 10:48, and yeah, please do these in-class problems as well after the break. All right, it's been 5 minutes, so please turn your cameras on, and we're going to talk about these in-class problems. So, does anybody have any idea on how you would try to do these problems? And yeah, if anyone has any ideas, then you can go ahead and speak up. Not then. Oh, so it looks like some people. Oh, okay. Um, well, I recommend everyone to attempt number two first, this one, because it's going to be a lot easier and more straightforward, as long as you remember how you do it. All right. So do people just not have an idea on what to do, or are they working? If you don't have an idea on number two, then I can give a hint. So, okay. So for number two, all we're doing is selecting 3 from 20, and the order doesn't matter, so it's just 20C3. And okay, I'll just wait for people to go and calculate it out. Hi, Paige, and we're just working on these in-class problems right now. If you, okay. Hi, Peyton. We're just working on these in-class problems right now. If you don't have an idea, then you can go and watch the recording after class. And then go. Okay. Well, okay. So this one is just simply going to be equal to 20 times 19 times 18 divided by 3 times 2 times 1. And again, the way you remember this is you have 20 ways to choose the first book, 19 ways to choose the second book, 18 ways to choose the third book, but now you have to divide by 3 factorial because the order does not matter. And if you calculate this out, you can get that's equal to 1140. So if you got 1140 on this problem, good job. Next one. A fair coin is flipped 10 times. How many ways are there to flip more heads than tails? Well, this one actually is a bit harder because the easiest way to do it uses a technique that I haven't told you before. So here's an idea. So just use symmetry. The number of ways to flip more heads than tails equals the number of ways where there are more tails than heads. So just think of it like that. And then you can use something like complementary counting. And then it shouldn't be too bad. Okay, so the way to do this problem is so in general, the number of ways you have to flip 10 coins is simply 2 to the 10 equals 1024. And you want to track the number of ways where the number of heads and the number of tails are the same. I think we may have used this technique on AMC problem as well. So so if the number of heads and the number of tails are the same, that means there are 5. And out of these 10, we just need to choose 5 of them to be heads. So 1024 minus 10 to the 5, well, 10 choose 5, which equals 1024 minus 252, which equals 772. So there are 772 ways where the number of heads and the number of tails are different. And the number of ways where there are more heads and tails will simply be half that, because the number of ways where they're different and the number of ways they're same are going to have to be the same amount. So you divide by 2 and you get the answer, which is 386. Does anyone have any questions on how these problems work? So now we're going to go on to another technique about counting. Okay, well, going to go on to the next one then. So we're going to use the technique that the book calls, and I think some people call sticks and stones, but it's more often called stars and bars. But it doesn't matter. All it matters is basically what it does and how it works, and it's pretty useful. It represents partitions with combinations. So what are partitions? Well, let's say you want to express 7 as the sum of three numbers. How many ways do you have to do this? Well, like for example, you could have 1 plus 2 plus 4, or 0 plus 3 plus 4, or 2 plus 2 plus 3, and so on. And we just want to count the number of ways you have to do this. Or it could also be 2 plus 3 plus 2. So it's a lot harder to count partitions that are like distinct. That means that you differentiate 1 plus 2 plus 4 and 2 plus 4 plus 1, but it is possible for you to count ones where you're just any order is fine. And I'll show you how with this example. Um, Uncle Henry has 10 $1 bills to distribute to his 5 nieces and nephews. How many ways does he have to distribute them? So if we think of each niece and nephew having a bucket like this, we need to put $10 in these buckets somehow. So if we, for example, have 2 in here, 1 in here, none in here, 3 in here, and 4 in here, then we want a way to represent this and to make it easier to count. How about instead of looking at these by the buckets, let's look at them as by the dividers. So if we instead, well, this is like sort of a bad explanation, but is it 5 kids total? Yes. It doesn't really matter. It's just the problem. So if you have something like this, uh, um, well, how many ways do you have to do this? If you, uh, we want to find a way to use combinations to describe this. And again, like in the case with the letter arrangements with the grid written up, we can use combinations to describe positions as well. Like, and if we take a look at these dots and the dividers, you can have something like this can be represented as this. Does everyone see how you went from here to here? It's clear that no matter how you distribute these, you will be able to convert it into something that looks like this, with 4 dividers and 10 dots. And for anything where you have 10 dots and 4 dividers, you'll be able to put it like here. So if we just choose a random one, like 0, 1, like I don't know, something like this. Uh, what you can see that this is equivalent to having the first one have 1, second one have 3, third one have 2, fourth one have 3, and last one have 1. And even if some of them have none, get none, like even if you have something crazy like this, um, then you can see that you have this is the same as having the second person get all of the bills and no one else. I received a question, why are we dividing it into 4 sections instead of 5? We are not dividing it into 4 sections, we're just using 4 dividers. There are still clearly 5 sections here. To the left of the first one, to the left of the second one, to the left of the third one, to the left of the fourth one, and to the right of the fourth one. And if we had 5 of them, then that would mark 6 sections instead. And the point that I'm getting at here is no matter how you arrange these 10 dots and 4 dividers, not 3, not 5, you will be able to get one a distribution. And therefore, we have 14 different positions here. We have to select 4 of them to be a divider. So the possibilities are just 14 divided by 4. Or 14 choose 4, I mean, sorry. And in general, if you have uh, n objects and k buckets, you are going to be looking for n plus k, n plus k minus 1, choose k minus 1. So in this case, uh, n equals 10, k equals 4, k equals 5 because 5 nieces slash nephews. So it's going to be 14. 10 plus 5 minus 1, and 5 minus 1. Does anybody have any questions on how this method works? If not, then I can try to come up with a different explanation. And this only works if people could have just one of them. But like, okay, okay, so let's pretend that instead of having 5 nieces and nephews, you have 5 buckets as shown here. And we you can represent these as stars and bars. That's where the name works. So if you just take a look at the dividers and put these in order, you can see, for example, that in this case you can get it into something that looks like this. And because you always have you always have 4 dividers between the 5 buckets and 10 objects. Uh, it'll always have 10 stars and 4 bars. Well, and uh, for everything that has 10 stars and 4 bars, you can turn it into a, a you can turn it into an arrangement, a distribution of these $10 bills. So if you then so before the first bar goes to the first person, or the first bucket, between the first and second goes to the second bucket, between the second and third goes to the third, and so on. And if you have 2 of them next to each other, then it's just going to have 0. Because of that, we can order these 10 stars and 4 bars in any way we want. And then we will be able to get something that looks like that. And does that make sense? And by the way, this is also equal to n plus k minus 1, choose n if sometimes that is more helpful. You can think of that instead as, for example, instead think of that as choosing the n star instead of the k minus 1 bars. So does that make sense? For this one specifically, it is still helpful for you to remember how it works in case you forget have or don't have an idea. But this one is useful to memorize, just like in general the concept. But now we're going to talk about some variations of the stars and bars concept. So it's placing dividers or bars to separate items or stars into categories, and you use combinations to choose where the bars go. Sometimes you will need to modify this concept by removing some stars or using complementary counting. So how many ways are there to roll a 7 with 3 6-sided dice? How many ways are there to roll a 13 with 3 10-sided dice? Hi. So, so I'm having some technical issues right now. Uh, okay. Should be back. Does everyone see the screen? Does everybody see the screen? Okay. Yeah, sorry about that. So, okay. So, I'll just go through these examples myself, but you'll often see similar things, and they will do something similar. So the first notable thing you can do this is uh, is to remove is if they require you to have at least one. And we'll talk about how you can do this. So, how many ways are there to roll a sum of 7 with 3 six-sided dice? Well, first of all, notice that. Oh, okay. It's not really wrong. But, so, six-sided dice, they obviously don't have a zero face. So, the smallest face here is just going to be a 1. So, that means that, unlike the normal case, you have to have at least one in each bucket. So how do we show that? Well, if we just put one or star automatically in there, then they can have zero all they want because like then you'll still have one and you're just going to add one to each number. So instead of having a roll of 7 with 3 six-sided dice, we're going to want a roll. We're going to have a sum of 4 with dice that goes 0, 1, 2, 3, 4, 5. And in that case, it becomes simple because now it's just stars and bars. With four, and this time you only have 4 stars. So an example is if you have them as stat like this, then the number of stars and bars you have are, oh yeah, 4 stars and 2 bars. But the roles that this would represent are 2, 3, and 2 because you're adding one to each one. Or if this wasn't here, then if your example had like this, it would be 3, 3, and 1. But but one issue with this that we'll run into with the next problem is that uh, what if it's going to be past the six-sided die limit? Like you can't roll a 7, right? Well, the good thing about this is that in this case you don't have to worry because with our modified set we need to get the maximum is 5 and we're just rolling 4. So even if like this one gets all of the stars, then it's still only going to be 5, which is well within our limit. So this would be 511. So we don't have to worry about this. And for this one, the answer is simply 6 choose 2, which equals 15. For the second one, how many ways are there to roll a sum of 13 with 3 10-sided die? So this is where it gets interesting. So again, like as like before, you cannot you can't end up with 0. So again, we're going to remove. Oh wait, by the way, does anyone have any questions about this process of like removing these stars from it? Uh, well, like if we wait, does anyone have any questions about stars and bars in general? I should say, or like, does anyone not understand anything specific? Uh, if you like don't understand, uh, you can either ask me or um you can ask like there are a lot of good online resources regarding counting like on apps. What is removal? It's not a technical term. It's just something that we did last time, where where because the maximum is 1, we just automatically put 1 star in each. If we just automatically put one of them, and sort of ignore the others. So I mean, an example of that would make more sense. What to explain is this one. If everyone has to have at least $1 bill, then then if we just give everyone $1 as a baseline, then we'd have $5 left to actually distribute. So that's the same as what we're doing right here. Uh, so for a roll of sum of 13 with 3 10-sided die, if we like give each of these 10-sided die a 1 to begin with, then then we have 10 left to distribute. So among these die, dice, which only go up to. So this case, we again have two dividers, but now we have 10 stars. So, for example, you might end up with something like this, which would represent getting a 4, 3, and 6. So this one is just 10 choose 2, right? Well, not exactly, because again, like before, you have to worry about going over. So in this case, it is actually possible to go over. And the maximum we can have in this case is 9, because if you have, well, okay, well, the only way that you can go over in this case is to have all 10 in the same box. If you have just 9 in one, if you have like 9 stars in one group, like this, and like one in here, this is still a valid roll. It's 10 to 1. It's when it's not, then all 10 of them are in the same one. So this is again using complementary counting, because this is a total number of ways, and we're subtracting the number of ways where it doesn't work, as in you have over a 10. So in this case, what that means is that all of them are in the same group. So there are only three possibilities here. Either you put them all in the first one, or the second one, or the third one. Why are there two divisors? Again, we have three dice, so we have three things between the left one, in the middle, and the right one. So anyway, 10 choose 2 minus 3, we get is going to be equal to 45 minus 3, which is 42. Does anyone have any questions about these? I know it's a bit like different and could be a bit confusing, since it's based on something that people still seem to have a little bit of trouble on, but you can ask. And if you want to improve like what you do, um I'll recommend I'll send a recommendation on Google Classroom, but um, Art of Problem Solving, which is the website I referred to in the first orientation class, has a problem solving tool called Alchemist, which basically is just gives you a bunch of which gives you some problems, and you can solve them, and it shows you how you did it or how it was wrong, and it can uh, it can like give you harder, easier problems and so on. Can I explain the last question again? Well, actually, I'll just send a link in the chat. So go check it out. Can I explain the last question? Yes. So, yeah. So, like before, you cannot have a 0. So if we start off by putting 1 in each, then we have 10. We have 10 numbers left to distribute. Um, among these three 10-sided die. So that would just be 10 choose 2, because you have 10 stars and 2 bars, and you want to subtract 3. The reason why you subtract 3 is because you can't have 11 1 1, or 1 11 1, or 1 1 11. So those are the three ones you can't have. Three possibilities. And I know my writing is very confusing, but there are three of these. So it's going to be 10 choose 2 minus 3, and that's where you got 42 from. And yeah, and using stars and bars, getting one of these is equivalent to having all 10 stars in one category. So that's another way you can see how there are only three ways where it can be. Does anybody have a question about this? Or does anyone still have any questions? If you're worried that you might go over, or that like I might go over while you're typing it, then you can just send a question mark, and I'll wait. If not, then we're going to um, talk about the in-class problems. So, how many ways can 12 pieces of candies be distributed to 5 kids? And a six-sided die is rolled 4 times. How many ways are there to roll a 9? So, just go ahead and try these problems. No. Some kids may not. It's possible that they might not get it. So that will make your calculation somewhat easier. So the first question is a straightforward application of stars and bars. So it's simply going to have 12 stars, which are the candy, and 4 bars, which are going to represent like the 5 kids. So it's simply going to be 16. 16 choose 4, which equals 16 times 15 times 14 times 13 divided by 4 times 3 times 2. So we're just going to here. So 2 times 5 times 14 times 13. And this will give your answer, which is, sorry, and this is going to give your answer, which is going to be equal to, I believe, 1820. Yeah. And for the second one, a six-sided die is rolled 4 times. How many ways did it roll? 9. Again, six-sided die, it has to be at least 1. And you'll notice that given that it's at least 1, um, it's actually impossible for you to roll to get more of them. So 1, 1, 1, 6 is going to you can't, like, even if those are all 1, then you're never gonna get 6. How did I get 16 choose 4? Again, that's 16. Well, you're choosing 4 bars out of 16 stars plus bars. So this one we have, in this case, we have, if we're removing 4 of them, we have 5 stars. Again, 9 minus 4 because we're assigning one of them already to each one. 3 bars because 4 minus 1 is 3, and you have 1 on each side. So it's going to be 8 choose 3, which equals 8 times 7, which equals 56. So and again, for this case, you can check that, in fact, you will always have enough. So does anyone have any questions about this? So I think someone put 12 choose 4 for this one. It's not going to be, oh wait, no. Someone put 12 choose 4 for the first one, I believe. The reason why that doesn't work is that you have to choose the bars and the stars. So it's 16 choose 4. We're choosing 4 bars out of the 16 positions, not 4 bars out of the 12 stars. So does that make sense? Uh, we can continue. So we're going to talk about Pascal's triangle. So if you've heard of Pascal's triangle or know what it is, then please send a private chat message. It's like I just want to see how many people here know what Pascal's triangle is. It's okay if you don't. So okay, looks like a few people have. So it's really simple. It's created like just like this. You start with a 1 on the top row here, and and every on the sides you always have 1 on each of them. On Okay, then each number is going to be the sum of the two ones above it. So 3 is 1 plus 2, 6 equals 3 plus 3, 10 equals 4 plus 6, and 20 equals 10 plus 10, 21 equals 5, 15 plus 6, and so on. So the way you create this is 1, 1, 1, 1, 1 plus 2, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 3 is 4, 2 plus 3 is 6, and so on. And uh, interestingly, if you look at grids, remember that you can represent it both as a combination, but also as a sum of the one to the left and one on the up, and on top of it, in this case, how many paths can we trace to each vertex on the grid? Well, to one, to these you can only have it one way. To here, you can either come from here or come from here. So it's 1 plus 1, 1 plus 2, 3 plus 3, and so on. And you'll notice that this is the exact same as Pascal's triangle. And well, you can pretty clearly see why that would be the case, because they're both constructed the same way. You add two numbers for each one, and on the side you always have ones. So, so that's interesting. So, and what this means is that there's a connection between Pascal's triangle and combinations, and there's actually a way to prove it. So I won't. Well, I guess I can get into it right now. So uh, I claim that if you have the nth number, if you have the rth number in the nth row, so this would be, for example, the one I've circled is the fourth number in the fourth row. This one is going to be equal to 4 choose 3. So 0, 1, 2, 3, 4, and there's the fourth row, starts from 0. And the way you prove this is that, well, you first look at the sides. The sides is going to be either equal to n choose 0 or n choose n. You clearly have y choose 3 because if this is a 0, 1, 2, this is a 0th number in the row. There's a first, there's a second, there's a third. But anyway, the sides are going to be n choose 0 or n choose n. And you can pretty clearly see why this is equal to 1. You only have one way to choose 0 items, which is to not choose any items. And there's only have one way to choose all the items, which is to choose all the items. And then what this means is we just have to prove that n choose r plus n choose r plus 1 equals n plus 1 choose r plus 1. And this is called Pascal's identity. So in this case, it would be showing that 3 choose 2 plus 3 choose 3 equals 4 choose 3. And the reason why this is the case, it's not really important, but if you think about choosing, uh, well, you can think about choosing 4 items, right? So let's, well, let's do this example. Let's use an example with slightly bigger. So this one would be 7 choose 3, and you want this to be 6 choose 2 plus 6 choose 3. If you have 7 choose 3, let's consider it like this. You have 7 objects, and you want to choose 3 of them. Consider the first object, and we're going to pretend this is special. So, let's use K-Circ. So this is, the number of ways you have to choose these is going to be 7 choose 3 by definition. But if the first one is chosen, then you have to choose 6. You have to choose 2 items from the other 6. So it's 6 choose 2. And Second case is if the first is not chosen, and in that case, you have to choose all the three items from the last six. So 6 choose 3. And these encompass all of them, so that's why this is the same. But anyway, that's all of that is just to prove that Pascal's triangle is the exact same as combinations. And uh, it's possible that Pascal's triangle, in some cases, will be easier to calculate than combinations, especially if you have to do a lot of them, because after all, when you're constructing Pascal's triangle, you have to make every row anyway. So if you have to calculate a lot of combinations, it could be a helpful guide. Like if you want to calculate, for example, 7 choose 2 plus 7 choose 3 plus 7 choose 4 plus 7 choose 5, it's a bit of a pain to like actually do all of that and calculate them by adding. But with Pascal's triangle, you just add these. I mean, multiplying. But with Pascal's triangle, you just add these down, and then there you have it. So because again, it's created as follows: 1 and then 1 and then sum of the two above it. Uh, so that's how Pascal's triangle works. And again, this is again the same as combinations. So you have to memorize it? No, you don't. You don't have to memorize Pascal's triangle at all because it's very easy to construct. Like, if I just have like a blank page, then the way you simply construct it is just you start with a 1, and then 1, and then 1. You have each side as a 1. You just add. 1 plus 1 is 2, 1 plus 1 plus 0 is 1, 1, and then 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 4 is 4, 3 plus 3 is 6, 3 plus 1 is 4. It's not memorization at all. It's just remembering the rule and just applying it. And this can be helpful in many cases, like 9, like this. But anyway, because it's 11:30, I'll give these Pascal's triangle problems as well. I'll give the first one just as homework, and the second one I'll show you how you do it. But uh, anyway, if you don't have any questions about Pascal's triangle or anything in class, then you can leave. You can leave the Zoom call. So if you have, so yeah, if you have any questions, then you can ask them. But if not, then see you later.